All right, welcome everyone. Today, we are putting on our detective hats to solve a chemical mystery, one that happens in beakers all over the world. Our mission? To uncover the real story hiding inside a chemical reaction. So let's open up our first case file.
Okay, here it is, our first case file. We've got an acid, hydrochloric acid, reacting with the base, sodium hydroxide, and it makes salt and water. Now, at first glance, it kind of looks like 4 different chemical characters are in the mix. But is that really the whole story? Or is there something else going on behind the scenes?
And that's the question, right? The one every good detective has to ask. When these things are dissolved in water, and that's what that little AQ symbol means, by the way, they don't just stay in these neat little pairs. So to figure out what's really going down, we've got to look a lot closer at the evidence.
Aha, and here is our first major clue, dissociation. You can think of it like a group of suspects just scattering the moment they hit the water. As soon as you put these compounds in, they break apart, splitting into their positive and negative ions. And let me tell you, understanding this is absolutely crucial if we want to figure out who the real players are in this reaction.
So how do we get a full list of everyone at the scene of the crime? Well, we've got a simple 3-step procedure for that. First, you identify all the aqueous compounds. Those are our main suspects. Second, you split them up into their ions so you can interrogate them one by one. But, and this is super important, anything that's a pure liquid, a solid, or a gas, you leave it alone. They're like indivisible units in this investigation.
Okay, so when we apply those rules, this is what we get. The full Ionic equation. It's basically a complete roster of everyone present at the scene. On the left, you've got your initial suspects, hydrogen, chloride, sodium, and hydroxide ions. Now look to the right. Something interesting has definitely happened. A water molecule formed, but, and this is interesting, notice the sodium and chloride ions? They look completely unchanged.
You know, this brings us to a really key concept in our investigation, spectator ions. Just like fans at a sports game, some ions are literally just watching from the stands. They're there at the beginning, and they're still there, totally unchanged at the end. They didn't actually do anything. They're just bystanders.
Okay, detective, your turn. Use those powers of observation. Take a good look at the reactants on the left and compare them to the products on the right. Can you spot which ions are just kind of hanging out, completely unchanged from start to finish?
You got it. The sodium ion and the chloride ion, they're our spectators. And since they didn't really participate, we can just remove them from our investigation. Let's clear the scene so we can focus on where the real action is. And there it is, the big reveal. When you clear away all the bystanders, you're left with this beautiful, simple, elegant equation. This is the net ionic equation. It shows us what really happened, what actually changed. A hydrogen ion and a hydroxide ion came together to form a molecule of water. That's it. That's the core of the entire reaction.
So this is the main takeaway from our investigation. For pretty much any reaction between a strong acid and a strong base, this is the true story. The spectator ions might be different. Maybe it's potassium instead of sodium. But the main event, it's always the same. A hydrogen ion meets a hydroxide ion, and they form water.
All right, you cracked your first case. Nice work. But you know, a good detective's work is never done. Let's tackle a new mystery, the curious carbonates. This time, we're reacting hydrochloric acid with sodium carbonate. And you'll notice we have a new product in the mix, carbon dioxide gas. Let's see if our detective skills hold up. Okay, let's run the same playbook again. We break down all the aqueous stuff into their ions. So the 2 HCl's become 2 hydrogen ions and 2 chloride ions. The sodium carbonate becomes 2 sodium ions and a carbonate ion. On the other side, the 2 NaCl's become 2 sodium and 2 chloride ions. But remember our rule. We leave the liquid water and the carbon dioxide gas alone.
So, can you spot the spectators this time around? Yep, it's the sodium ions and the chloride ions again. So when we remove them, we get this net ionic equation. 2 hydrogen ions react with a carbonate ion to make water and carbon dioxide. Case closed. Or is it?
You see how this works? Solving one mystery often just reveals a deeper one. We know that acids react with bases, but why is sodium carbonate considered a base? It doesn't have that OH hydroxide group we saw in our first case. So what's the deal here? And the answer? Oh, it was hiding in plain sight this whole time. It's right there in our net ionic equation.
Look closely. The carbonate ion is accepting the hydrogen ions, the protons, from the acid. And what is the very definition of a base? It's a proton acceptor. So the net ionic equation didn't just simplify things, it proved the true chemical identity of the carbonate ion. Amazing, right?
Okay, so let's recap what we've added to our chemical detective toolkit today. We learned that net ionic equations are awesome because they strip away all the distractions and show us the main event, the core chemical change. We do that by finding and getting rid of those spectator ions. And through this, we've uncovered two huge truths. The neutralization of a strong acid and a hydroxide base is always about forming water, and carbonates are bases for a very simple reason. They accept protons.
So we've seen how looking just a little bit closer can reveal the real story behind a chemical reaction. It really makes you wonder, right? What other hidden reactions are out there, happening all around us, just waiting for a good detective to come along and uncover the truth? Thanks for joining this explainer.